Okay, so far the work we've done is comparing two sets of data when they were quantitative data, such as we compare two sets of data for the proportion, found difference in proportion, or we found difference in mean. But sometimes you have larger groups of data or multiple sets of data that you want to compare. And for that, we need a different type of analysis, and it's an analysis of variance. So let's see why we have this. Two data sets are shown below, both with Group A and Group B. And we are testing for a difference in population means between the two groups. The sample means are the same in both cases. Are we more likely to find a difference in population from the data in data set 1 or in data set 2? So let's kind of look at this. So if the next value is 31, can you tell which group it is in for data set 1? Can you tell which group it is in for data set 2? This is what we should ask ourselves if we're trying to see if there's, in which group will we more likely find a difference in population. So we want to see in which case is it easier to tell whether the value is more likely to be in Group A or Group B. The easier it is to tell the groups apart, the more likely we are to find a difference in population means. So let's look at them. So we're going to look at data set 1. So the groups or populations seem to be clearly different. In data set number 2, there is so much random variation it is very hard to tell whether there is any difference between group A and group B. That is why variation within groups matters. And if we look at that, we see with group A in data set 1, they're all kind of grouped between 19 and 21. Group B, they're all grouped between 29 and 31. Yet in group A of data set 2, we have a low of 5 and a high of 31. In group B, we have a low of 19 and a high of 39. So there's much more variation in group A and group B in data set 2 than in group A and group B in data set 1. So we are much more likely to conclude that there is a difference in population means between group A and group B in data set 1. Okay, so now we have data collected on the heights of singers summarized below. We have mean, standard deviation, and sample size for the 4 main voices of singers: soprano, alto, tenor, and bass. Heights are in inches. Does average height differ by voice? And we want to show all the details of the test. So the standard deviation condition is met. They're all around the same. So standard deviation condition is met. So H sub 0 is the 4 population. Means are the same. And HA at least 2 of the population means are different. So what we need to do is set up our table for the calculations. And we are going to use another new statistic, the Fstatistic. So we have the source of the data, the degrees of freedom, what's known as the sum of squares, the mean squares, and the Fstatistic. So within the groups, the degrees of freedom is the number of groups minus 1. So it'd be 4 minus 1 or 3. The sum of squares, call it SSG. To get the SSG, you have a sum. You take the sample size times the group mean minus the total mean squared for each group. So we have 36 times 64.25 minus 67.12 squared, plus 35 times 64.89 minus 67.12 squared, plus 20 times 69.15 minus 67.12 squared, plus 39 times 70.72 minus 67.12 squared. And when we do this calculation, we get 1058.44. Now we have error is our second source of data. The degrees of freedom are n minus k, where k is the number of categories. Or number of groups. So this would be 130 minus 4, or 126. For this, we do a calculation called SSE. And SSE, we take the sample size minus 1 times the standard deviation squared for each category, and then add them together. So for the second one, we have 35 minus 1 times 2.795 squared. Then 20 minus 1 times 3.216 squared, plus 39 minus 1 times 2.361 squared. And when we do that calculation, we get 796.73. Now we have our total. So total degrees of freedom is sample size minus 1. And now we get an SS total calculation. And this is the sum of the two previous ones. So it's SS for groups plus SS for error, which is 1058.44. So sum of squares for groups, sum of squares for error, plus 796.73, which gives us 1855.19. Now we need to get the mean squares for the first two groups, for groups and errors. So mean squares for groups is the sum of squares for groups divided by the degrees of freedom. So that would be 1058.44 divided by 3, which is 352.813. Then we need the mean squares for error, which is the same thing. It's the sum of squares for error divided by the degrees of freedom. So that's 796.73 divided by 126, which is 6.323. Now for the F statistic, it's the mean squares of groups divided by the mean squares of error. Which is 352.813 divided by 6.323, which is 55.798. So this is our F statistic. So our F statistic is very large. So we expect a small p-value. So to get the p-value, we use FCDF. It's right tail, so it's our test statistic. 999. Then our degrees of freedom for groups and degrees of freedom for error. So it's under second vars, FCDF lowers 55.798. Upper is 999. Degrees of freedom for the numerator is 3. Degrees of freedom for the denominator is 126. And when we calculate it, we have 5.120 E negative 23. So it's essentially 0. So we reject the null hypothesis that the four population means are the same. And we conclude that there is very strong evidence that mean height differs between the four types of singers. We should note that gender is a very strong confounding variable. And we want to note that because the higher voices, alto and soprano, are generally females, and females are generally shorter than males.